Okay, good morning all of you. Let's get started. Professor Amlan, you want to add something?
Not right now. Good morning. I will add comments later.
Okay, this is where we stopped yesterday. Okay, under reinforced section, balance section, and over reinforced section. Once you know the dimensions or size of the beam, how to arrive at the area of steel. Any questions here?
Sir, I have a confusion.
Tell me.
So when we say redesign this under reinforced or redesign this over reinforced beam, what are we doing? What are we trying to achieve after redesigning?
What redesigning? Oh, redesign. Okay.
Yes.
Please note that. Please note that we are taking the same dimensions or one of the for the same moment carrying capacity. Please note that all the problems are solved for the same moment carrying capacity of 150,000 Newton meter. That is what is meant by redesign. And B is maintained at 250 mm, and only depth is changed. Okay. Redesign in the sense, I don't want to repeat the entire problem statement. That's why it is mentioned as redesign. And the idea of doing for the same moment carrying capacity is to see what difference it makes. What is, because we want to compare. If I design it as under reinforced, what is the amount of steel? If I design it as a balanced section, what is the amount of steel? And if it is designed as an over reinforced section, what is the amount of steel? To get a feel for it, because same problem is solved as in all these cases, and same thing. Even today's class, we still use the same example: 150 kilonewton meter. Sorry, 150,000 Newton meter, and then we try to solve using. In today's class, we learn how to do doubly reinforced section. Okay. Any questions? And let me recap what we have discussed yesterday's class, because that is required to proceed further in today's class. In yesterday's class, we discussed about over reinforced section. Over reinforced section, actually, the situations or the reason why we go for over reinforced section is because of the constraint on the depth. Yesterday we discussed one way of handling this, or when you have constraint on the depth, when the effective depth is reduced, effective depth whatever is required for a balanced section, if you are unable to provide that, and if your effective depth the restrictions are such that effective depth is less, then both the stress in steel as well as stress in concrete are going to increase. One way to bring down the stress in steel is to add nominal additional reinforcement area, so that stress in steel is going to come down. But stress in concrete is going to still remain high, or it may exceed its permissible limit. So another way of bringing down is increase the area of compression. Increasing area of compression, one way of doing it is by adding some more amount of steel, so that the neutral axis depth is going to come down, and it increases the area in compression. And that actually the logic for that is coming from the simple equation or simple concept that we noted, that the moments of area in compression, moment of area in compression about the neutral axis should be equal to moment of area in tension about the neutral axis. Using that relation, once you increase the area of steel, N can also be increased, or the neutral axis depth you can bring it down, and so that the area in compression increases. But yesterday we noted, when we Again, when we redesigned that same beam problem, having moment carrying capacity of 150,000 Newton meter, we noted that for a decrement of 8%, approximately 8% of the depth, we need to actually increase the amount of steel by almost 63%. That's what we noted in yesterday's class. Okay. So now in today's class, so there is a restriction on the depth, but I don't want to design it as an over reinforced section. What is the other option? You please note that how we actually brought down the stress, the compressive stress in the extreme fiber and concrete to a reasonable value below or equal to its permissible limit in over reinforced section is by increasing the amount of tensile steel. That is what we did. But the other way of doing it is, since the amount of concrete area in compression is less, we can compensate it by adding some amount of steel in compression region as well. Okay. So that is what we are going to do in today's class. That is what is doubly reinforced section. Okay. Any questions? So let me go further. Design of rectangular RCC beam with compression steel. Okay. Just 1 second. Let's go through this. Although concrete is usually cheaper for carrying compression than steel, compression steel may sometimes have to be used. Okay. Such sections, called doubly reinforced sections, becomes essential for the following cases. When the dimensions of a section have to be limited for architectural reasons, so that the moment to be resisted is larger than QBD square. QBD square is nothing but for a balanced section. Larger than QBD square for singly reinforced balanced case of the section. Okay. So when there is a restriction on the depth from architectural considerations or some other considerations, one way of doing it is yesterday whatever we discussed, design it as an over reinforced section, or the other way of doing it is adding compression steel. So we'll see in today's class how to do that. So the other reason why it may be required is the moments. When the moments are when the members are subjected to alternate external loads and there is reversal of bending moments. When there is reversal of bending moments, then also it is better to go for a doubly reinforced section. Okay. When the members are subjected to loading eccentric on either side of the axis, such as in columns subjected to wind loads. Please note that don't be of impression. And when members are subjected to accidental lateral loads, shocks, or impacts. Okay. The compression steel increases the toughness of a beam and reduces possibility of a sudden type of failure. It also reduces creep it also reduces the creep and shrinkage deflection of a beam. Okay. Creep and shrinkage deflection of a beam. In actual cases, if depth is less than 95% of balanced depth, it is more economical to design the section as doubly reinforced section or doubly reinforced one. Okay. So yesterday you got a feel, if you really followed the example that we looked at, for 8% decrement of depth, the amount of steel, if you design it as a singly reinforced section, the amount of steel that you need to provide is tensile steel that you need to provide is increased by almost 63%. Okay, so it's not really worth or economical to design it in that way. So in that case, we can actually design it as a beam with compression steel. Okay, so any questions here? So let's see how we are going to do it. Please note that we know what is the moment this beam has to withstand, or what is the targeted moment carrying capacity of the beam. Okay, and so the idea here, how we proceed is, we know whatever moment, our target moment carrying capacity, and we will see how much, if it is designed as a balanced section, how much moment it's going to resist. Okay, how much moment it's going to resist if it is designed as a balanced section. And then what is the difference between the target moment and whatever moment that this balanced section can take. So that difference, for the difference amount of moment, we are going to provide additional compression steel as well as additional tension steel, because please note that the resisting moment is going to be the resisting moment is going to generate only if you have equal and opposite forces separated by a lever arm. So whenever you compensate the compression region with a compression steel, some amount or some equivalent amount of tensile steel has to also be provided, so that additional moment can be generated, additional moment of resistance can be generated. Anyway, this is the procedure we'll be following. So let's see. So this is the section. It is whatever I tried to explain orally.
There is one question. Can you just read that question and answer?
Why will the moment increase if the dimensions are restricted? Please note that moment is not increasing. Moment is not increasing. When you restrict the depth, what is going to happen? Your lever arm distance is also going to reduce. Lever arm distance is going to reduce. How the resisting moment is generated? Resisting moment is generated by the tensile and compressive forces separated by this lever arm distance. Once the lever arm distance reduces, your moment carrying capacity also reduces. So it's not the moment. The applied moment is 150. Please note that in all the examples, that's why the applied moment or the targeted moment carrying capacity is taken as 150,000 Newton meter. Whatever the moment that this beam has to resist, it remains same, but the moment carrying capacity of the beam reduces when the depth is reduced. Okay, so this question, I think you are now I think anyway you understood it. So let's go further. Any other questions? So here there are some restrictions on the depth. Okay, and let's understand this whatever is shown in this figure. So we are going to design a doubly reinforced section. So doubly reinforced section means you are going to have some amount of steel in compression as well as amount of steel in tension. So the steel that is in compression is denoted with A, capital A, SC, and the steel in tension is denoted as AST, and other things are all I think you are familiar with all this notation. B is the width of the section, D is the effective depth, and please note that when we have this compression steel, we need to also know what is the stress. What is the stress in concrete? What is the stress in concrete at the level of compression steel? From which we can calculate what is the stress in steel at that level. Okay, stress in this the compression steel. So that's why we need to note down this the cover thickness for the compression steel. That is what is denoted with this. This is actually not D. It is a D prime, small d prime. Okay. So small d prime indicates you the cover thickness for the compression steel. Okay, and so how the procedure or how we go about designing this section? We design it if it is a balanced section. If it is designed as a balanced section, what is its capacity? We'll try to find it out. And we know what is the moment this has to resist, this beam has to resist. So whatever moment carrying capacity of the balanced section, the difference between the moment it has to resist and the balanced section moment carrying capacity, we are going to find it out. For that, we are going to put some additional compression steel and additional tensile steel. So that is what is written here for the balanced moment. Okay. So we'll see all this. And how do you get this additional steel? Additional steel for this balanced moment, that is given by this equation. Additional steel for additional compression steel for whatever additional moment it has to resist. That is given by or it is calculated based on stress at this level. We'll see all that in a while. Okay. So let's proceed further and other things. I think all this stress distribution diagram, everything is all self-explanatory. Okay. So this stress here, stress in the extreme fiber in concrete is denoted with sigma CBC, and the stress at the level of compression tensile steel. Here at this level it is going to be sigma ST prime divided by M, and here at this level the extreme fiber stress here, this is actually the stress in the steel in the extreme fiber. Okay, anyway, forget about this. You can take this one. Okay, sigma prime ST divided by M. So let's see the procedure for a given dimensions. Let's stick with whatever problem we are looking at. Let's take the same dimension. Let's redesign. Let me use the same word, redesign. Whatever beam we are looking at, redesign the beam, which you actually this one here. Redesign the beam with B is equal to 250 mm and D is equal to effective depth is equal to 650 mm, and the target moment or the moment which this beam has to withstand is 150,000 Newton meter for two types of steel, Fe250 as well as for Fe415. Okay, so redesign this beam as a doubly reinforced section. Quickly take a note of this. B is equal to 250, D is equal to 650 mm, M is equal to 150,000 Newton meter, and in case of Fe250 steel, D is 650 mm. And in case of Fe415 steel, effective depth is taken as 750 mm. And please note that both the 650 mm and then 750 mm both are less than the depth that is required if it is a balanced section. Okay, so now let's see what is the procedure. So if dimensions are given, B is equal to 250, D is equal to 650 mm. Let's discuss for one of the steels, Fe250 steel. So for that steel, for that dimensions, if it is a balanced section, what is the moment carrying capacity? That you can easily find it out once the grade of concrete is fixed, once the grade of steel is fixed, Q is fixed. So moment carrying capacity, if it is a balanced section, for those dimensions, you can easily find it out. And also once this MC is known, area of steel for a balanced case also can be found out. Either using this formula or you have already seen a chart where we prepared Q balance and P balance. You can read P balance, percentage of steel for a balanced section, and then multiply with the cross-sectional dimensions, then you get the area of steel. That way also you can do it, okay? So this is the steel that is required if it is a balanced section. And now, but the moment carrying capacity for a balanced section, MC is less, is going to be less than our targeted moment. Our targeted moment is 150,000 Newton meter in this particular problem we are going to look at. So M, the balance moment, the difference between these two you denote, or that is what is denoted with this MS. MS is M minus MC. Target moment minus the moment if it is designed as a balanced section. And that moment is noted. And this is the additional moment this beam has to resist. For that, what is the amount of tensile steel? For that, what is the amount of tensile steel I need to provide? That can be obtained using this relation. Please note that this is the additional moment. And you just go back to your, this one, M is equal to the moment that is resisted by the tensile steel. M is equal to area of steel multiplied by permissible stress in steel multiplied by lever arm distance. And here, this is the balance moment. And for this moment, I need to provide additional tensile steel. So the area of additional tensile steel is obtained as MS divided by permissible stress in steel multiplied by lever arm. What is the lever arm? Lever arm here is the effective depth, the additional steel that you are providing, additional tensile steel that you are providing, additional tensile steel that you are providing is going to form a couple with the compression steel. Compression steel depth is D prime from the top. So the lever arm between the compression steel and additional tensile steel that you are providing. Additional tensile steel that you are providing, or I think that figure is not shown here, or here it is shown. Additional tensile steel that you are providing, the lever arm is D minus D prime. Okay, so the additional tensile steel is given by the balanced moment divided by permissible stress in steel multiplied by the lever arm distance. And this is the steel, tensile steel that you need to provide if it is a balanced section. And this is the additional tensile steel. This is denoted with AST1. This is denoted with AST2. Total amount of tensile steel that you need to provide is AST1 plus AST2. Please note that it is not just enough to provide this additional tensile steel. You need to provide additional compressive steel in compression. Then only you are going to have additional moment of resistance generated. Okay. So what is the amount of compression steel that I need to provide? That we will be seeing in a while. And meanwhile, the depth of the neutral axis for a balanced section. Depth of the neutral axis for a balanced section can be obtained from permissible stress in concrete, permissible stress in steel. And here neutral axis depth fact, or the neutral axis depth is for a balanced section is noted here. N is equal to sigma CBC divided by sigma CBC plus sigma ST divided by M multiplied by D. So everything is known here. So you can calculate neutral axis depth for a balanced section. once you get neutral axis depth for a balanced section, we can actually find the stress in concrete at the level of compression steel. Stress at the level of concrete, stress at the level of compression steel. Stress in concrete at the level of compression steel, that we can easily find it out from this linear distribution of stress. Stress is varying from 0 here, and stress here is permissible stress in concrete, which is sigma CBC. What is the stress at the level of compression steel? That you can easily find from this linear variation. Okay, it's going to be sigma. Let's denote this stress at this level as sigma CBC prime. Sigma CBC prime is going to be sigma CBC divided by n multiplied by n minus d prime. So that is how you can actually find the stress in concrete at the level of compression steel. And if I want stress in steel, stress in compression steel at this level, once you get the stress in concrete at the level of compression steel, you can multiply it with 1.5 m minus 1. 1.5 m minus 1. Okay, so that is actually what is written here. The additional compression, the additional compressive force that is generated because of this compression steel, that is what is denoted. There is a typing mistake here. It is written as 15. It should be 1.5 m minus 1 times sigma CS. CS is nothing but sigma CS is nothing but stress in concrete at the level of compression steel. And this is going to be this 1.5 m minus 1 sigma CS is going to be the stress in compression steel multiplied by area of compression steel. And what is the additional moment that is generated because of this compression steel? This additional compressive force multiplied by the lever arm. So based on that, we can calculate what is this area of compression steel. Okay, so let's see that stress in concrete at the level of compression steel. This is what I mentioned. So you need to calculate this sigma prime CS. Sigma prime CS is sigma CBC divided by n multiplied by n minus d prime. And this value of stress, this is the stress in concrete at the level of compression steel. And if you want stress in compression steel, you need to multiply this with 1.5 m, because code is saying for compression modular ratio, you increase it by or multiply it with 1.5 times. And minus 1 is because some amount of concrete is replaced by the steel. That's why minus 1. So 1.5 m minus 1 times this is going to give you stress in compression steel. Once you know stress in compression steel, and once you know the lever arm here is the distance between the compression steel and the tension steel, which is d minus d prime. You can see here d minus d prime is the distance between the compression steel and the tension steel. So you need to use that lever arm, and ms is nothing but the balance moment, that additional moment it has to resist, and based on that you can calculate compression steel. Okay, so you got additional tensile steel you got here, and that additional tensile steel you add to the tensile steel that is required for a balance section. Then you are going to get the total amount of tensile steel, and you now calculated what is the compression steel you need to provide. Already you know the B and D dimensions, so the entire design is completed. Okay, and now whatever amount of compression steel that you got. I told you yesterday, each of like 100 students in the class, 100 students can come up with the different dimensions, different amounts of steels. So how do I check which one, whether is a, can we have a self check? So that self check can be made like this. A check can be made either by obtaining ASC by moment. You can also obtain ASC, area of compression steel, by equating moment of total area in compression to moment of total area in tension. And then you can compare, okay? So that is what is mentioned. A check can be made either by obtaining ASC by moments, by moments of the areas about the known position of neutral axis and comparing with the value obtained using this relation, or by obtaining position of neutral axis from the known value of cross section and the compression steel, this tensile steel that you just now obtained, and comparing the value with the balanced depth of neutral axis. Please note that finally the neutral axis depth should match with what you get from balanced section, because we are not disturbing that. We are still designing it as a balanced section, okay? And then and finally it's not going to remain as a balanced section, because once we modify this effective depth to match to take into other cover thickness and other things, by taking all those into account and rounding off to the nearest some higher side, some round number, the effective depth is going to increase. That is a different issue. But here at this stage, we are designing it as a balanced section. So finally, whatever neutral axis depth that you get here, whatever neutral axis depth that you get here by equating moments of areas in compression to moments of areas in tension, that has to match with whatever neutral axis depth that is for a balanced section. And one more thing, whatever amount of steel that you provided here, compression steel, code is putting some restrictions on this. And it is also given this, whatever we are going to discuss about this restriction of the compression steel, that is also given in code IS 456 page 47. So let's read this. The percentage of steel in compression calculated from this one, ASC divided by B, and please note that here it is overall depth. ASC divided by BD times ASC divided by BD times 100 should preferably not exceed 4%. And if it exceeds 4%, then whenever you are doing calculations, for calculation purpose, you take it as 4%. If it does, if the percentage of steel exceeds 4%, only 4% should be allowed in the calculations for the resisting moment of beam. So let's see in the code where it is given. Yesterday we have seen here, page 47, maximum area of compression reinforcement shall not exceed 4% in the sense 0.04 B times capital D. Capital D is the overall depth. The compression reinforcement in beams, anyway, this is a different issue, okay? So the maximum area of compression reinforcement is restricted to this one. And if it exceeds, if suppose already existing beam is there, if it exceeds 4%, for your calculation purpose, you take it as only 4%, okay? So anyway, let's see a numerical examples. At the after going through that examples, if you have questions, we'll discuss, okay? So let's redesign the same beam, taking B is equal to 250 mm, D is equal to 650 mm, FE 250 steel, and D is equal to 750 mm for FE 415 steel. So now the workout here, whatever is the workout that is shown here is for B is equal to 250. Please take a note of that in your notes. B is equal to 250, D is equal to 650, small d, and FE 250 steel, and the cover thickness for the compression steel, that is 50 mm. And permissible stress in concrete, permissible stress in concrete and bending compression is 7 Newton per mm square. Permissible stress in steel, which is Fe250, it is 140 Newton per mm square, and M is equal to 30, modular ratio is equal to 13. And once these are decided, you can go back to your basics or the chart, the table that we prepared. You can go and read there. For this, what is the neutral axis depth factor, K, for a balanced section? That is also noted. Please take a note of this. And for a balanced section, what is neutral axis depth factor? For a balanced section, what is the resisting moment factor? For a balanced section, what is the lever arm factor? That is all noted, because these are all fixed once the grade of concrete is fixed, once the grade of steel is fixed. And then you calculate what is the moment carrying capacity for a balanced section with these dimensions, with the dimensions of B is equal to 250 and D is equal to 650 mm. For this grade of concrete, for this grade of steel, what is the moment carrying capacity for a balanced section for those dimensions and this steel and this concrete? And that is what is noted here. And what is the amount of steel for this moment? Moment divided by sigma st multiplied by JD. J is a balanced J, and D is, I told you, D is small d is 650 mm. So please check whether these numerical values are correct or not. So this is the area of steel that is required if it is designed as a balanced section, and this is the moment this balanced section can withstand. And what is our target moment? Target moment is 150 Newton meter or 150,000 Newton meter or 150,000 times 1000 Newton mm. So the difference between that moment and this moment, that is noted. So this is a balance moment. Balance moment means the moment, the additional moment this beam has to withstand, we need to take care of that. For this additional moment, what is the amount of steel that is required? Tensile steel. Moment divided by stress in steel, permissible stress in steel, multiplied by lever arm. Lever arm distance here is going to be lever arm distance between the compression steel and the tension, this level of tension steel, at the position of tension steel. So that distance is going to be effective depth minus cover to the compression steel. Cover to the compression steel, D prime is given as 50 mm. So effective depth is 650 minus 50. So this is the additional tensile steel. So total amount of tensile steel is AST1 plus AST2. Okay. And now we need to calculate.
There were a few questions. Can you please take the questions?
Yes. Why did we take lever arm distance D minus D prime? Shouldn't we take a point of application of total compressive force? Please note that this lever arm distance D minus D prime is for the additional tensile steel and the compression steel. That distance is already fixed. Fixed in the sense the position of tensile steel is at a distance effective depth from the top fiber in concrete, and the position of compression steel is at a distance D prime from the top fiber. So that is taken. For this, please note that this D minus D prime this D minus D prime lever arm distance is used to calculate the amount of additional tensile steel and the compression steel. Okay. the additional tension, additional tensile force, you can also think that the distance between additional compressive force or additional tensile force and the additional compressive force because of this compression reinforcement is d minus d prime. Okay, and the next question is earlier percent of steel we used effective depth, but now we used overall depth. Why? Okay, this is compression steel. Okay, this is compression steel. So when you are in compression, concrete is good in compression. Concrete is good in compression as well as in tension. So sorry, concrete is good in compression, whereas earlier tensile steel, concrete is not good in compression. That's why the whatever additional cover is not taken into account. So now, since concrete is good in compression, overall cross-sectional dimensions are taken. Okay. So
let me. Can I just interpret it differently? See, this maximum amount of steel is based on the construction convenience. Later on, when we see the design of columns, we shall see that maximum amount of steel is 8%. And please note the steel is always placed towards the edges. Now, if there is more amount of steel, then concreting gets difficult. And hence, in each phase, the maximum amount of steel is specified. Now, this provision is based on the total cross-section and it's nothing to do with the flexural analysis. And hence, the effective depth is not used. It is the total depth is used so that we know what is the maximum amount of steel permitted based on construction convenience. Okay.
Okay, any other questions? One more question. Will KQP be same for a section of any dimensions as long as, yeah, it is same. Please note that K is neutral axis depth factor, Q is the resisting moment factor, P is the percentage of tension steel. And please note that we have already noted all these relations. They are not going to be, they are all dimension independent. Okay, they are all dimension independent. So they are going to be same irrespective of whatever dimensions, as long as it is a balanced section. Okay. So now let's proceed further. So this is the amount of steel. AST1 is the amount of steel that is required for a balanced section. AST2 is the additional steel that you need to provide to take care of additional moment that the beam has to resist. And not only this addition, so total amount of tensile steel is AST1 plus AST2. And it's not enough if you provide additional tensile steel, you need to provide additional compression steel to generate the additional moment of resistance. So how to do that? How to calculate this additional compression steel? For that, we require what is the stress at the level of compression steel. Stress at the level of compression steel can be obtained from stress in concrete at the level of compression steel. So stress in concrete at the level of compression steel, sigma prime CS, can be obtained using this relation, sigma CBC, n minus b prime divided by n. This is simply based on linear interpolation of stress distribution in the compression region. So this gives you stress in concrete at the level of compression steel. So if you know this, what is the stress in compression steel? It's going to be 1.5 m minus 1 times this is going to be the stress in compression steel. So that is what is written. So area of compression steel is additional moment divided by stress in steel in compression, which is 1.5 m minus 1 times sigma prime CS multiplied by the lever arm distance. Lever arm distance is, for compression steel, lever arm distance is the distance from the compression steel position to the tensile steel position, that is D minus D prime. So that gives you area of compression steel. So now the beam dimensions are B is equal to 250, effective depth is equal to 650, tensile reinforcement area is 880 mm square. This is mm square. There is a typing mistake. And the area of compression steel is 371.38 mm square. And now I want you to compare. I want you to compare this 880 mm square with the amount of steel that you got for a over reinforced section. What is the amount of steel that you got for a over reinforced section? Because the same beam we designed it as an over reinforced section. The amount of steel for D is equal to B is equal to 250, D is equal to 650 to resist moment of 150,000 Newton meter for over reinforced section. The amount of steel is this much, tensile steel. And now you see the amount of steel, it is far less than that. The amount of steel is far less than that. This one, 880. It's almost 1000 mm square less. Okay? So it's not economical to design it as a over reinforced section. Instead of that, you can design it as a doubly reinforced section. So this is how you arrive at the tension steel area, compression steel area, and and that is what is mentioned here. Okay, if it is over reinforced section, this is the area of steel that is required. Okay, and now to check whether this area of steel that you obtained is correct or not, you can calculate the neutral axis depth by equating moments of area in compression to the moments of area in tension, and you check whether this neutral axis depth is matching with the balanced section neutral axis depth. Okay, and also now you know the moment, and also you know the cross-sectional dimensions. So now you can even find m divided by bd square and compare with balanced section. Balanced section resisting moment factor. That is what is done here. This is just for checking. Okay, this is just for checking. And the same calculations are repeated with Fe415 Okay, so you go through this and cross check if there is any mistake in the numerical values. Any questions here? Professor Amlan, you want to add something? And in tomorrow's class, in the next class, we will be studying about flanged sections. We'll be studying about the flanged sections, design of flanged beams.
Okay, I'm just repeating whatever was mentioned. So in designing for a doubly reinforced section, we are starting with the depth of the neutral axis for a balanced section. The reason is we are trying to utilize the concrete in compression as much as possible. And then whatever extra moment requirement is there, that is being satisfied by the extra steel in the tension side and some steel in the compression side. In this way, that means if we start with the depth of neutral axis of a balanced section, then the total amount of steel comes out to be an economical value. It is not like arbitrarily picking up some additional steel in compression and tension. We are starting with the depth of the neutral axis corresponding to a balanced section to make the section economical. Okay.
And one more comment is there here. Some slides which SAR is teaching are not there in the file uploaded on Moodle. Please note that you need to keep, you cannot simply download that file on Moodle at one time and then start reading it. What I suggest is after the class is over, whenever class is over, I'm uploading the new file with the same name. Okay, so you make use of the latest file that is available on the Moodle. Okay, so I know that I'm modifying some of the slides because I keep changing the slides depending on how much we progress and what topic I want to cover. Okay, so you please keep a watch on the latest slides on the Moodle. Any further questions or comments? Okay, then we'll meet tomorrow's class.